Hello, my name is Alexander and you are currently watching the DP Labs channel. I've already briefly mentioned in a previous video that the very first scooter I ever built has now come in for some much needed maintenance. Now I want to fix the shortcomings and issues that were present in the original design of the scooter. In this particular scooter, the cooling system was actually devised and implemented only after I had already finished designing the frame. And because of that, the weak point or the main vulnerability of this construction is specifically the sealing of the hose inlets through which the coolant circulates. Now I want to modify the motor to completely eliminate this problem. The Chinese stator that was in the hub motor, which I bought for this project, originally had a power of 800 watts, and I upgraded it by installing an additional radiator inside. At its peak, I was able to get 12.4 kilowatts out of it. For circulating the coolant, I carefully drilled the axle right here at this spot to go under the bearings. I drilled the axle right here for the fluid to pass under the bearing and the oil seal, and here is the outlet hole. On this side I drilled a hole like this, through which the wiring passes, and I also stuffed a second hose in here so the coolant could circulate inside the engine. This particular spot needed to be sealed. The outlet hole is very close here, and there's too little space to fit an oil seal. This is likely normal. I decided to make this particular spot exactly the same way as on the new scooters. We made a bushing like this. Both the coolant hoses, the phase wires, and the hall sensor wires will pass through it. Now those holes that were there, we'll fill them with epoxy resin so that the oil seal is fine. We made a bushing, sealed the holes and pressed it in. The bushing and all the wiring will go through it. This is the original cover with a small bearing which fits right onto this axle. But to install a bushing like this, you need a larger bearing diameter with an inner diameter of 30 millimeters. Here on the cover, the seat is 17 millimeters, so the entire cover needs to be reworked. It will fit in here like this, and here there will be protective bearing and oil seals. Today I really want to finish working on this cover. Right now. Yesterday I machined one side of it. And today I need to continue working on the other side so that it looks about the same. And then send it for lathe work so that all the seats for the oil seals and bearings are properly machined. This is specifically the second part of the engine. Finishing the cover, then machining. We did a bit of work here. We'll also need to properly install a protective oil seal here to protect the bearing. We did a bit of work here. We'll also need to install an oil seal here to protect the bearing from the coolant. In the first version, transformer oil was originally used as the coolant. The thinnest possible oil, meant for Arctic transformers, was chosen to ensure faster circulation because with thicker oil the pump just can't handle it. The diameter of the hoses that can be threaded through this shaft is very small, and thick oil just pumps too slowly. This is a 3D model of the future cover. Right now, I'm creating vectors to define the machining area for writing the control program. It's not a particularly complicated process, just tedious. You have to consider all the nuances so you don't ruin the workpiece or damage the cutting tool, or even the entire machine itself. I think some of you might actually be interested in seeing in more detail exactly how the actual work process happens. Today we'll try to film the process of machining the cover for the engine from the back side as thoroughly as possible. The main character
is this Chinese machine. My little fish, my strawberry.
A hard worker. Unfortunately, it's not doing well anymore. I've exhausted the ball screw's lifespan. The design here is, unfortunately, really quite unfortunate. The servo drives are actually too powerful, and the ball screw supports are very flimsy and not robust. I have already ordered new ball screws and proper sturdier supports. We will machine the ends on the lathe mill Haas machine and then replace everything that needs to be upgraded. I think this will significantly improve the overall accuracy class of this machine. We'll see in practice just how much. The first thing to do after turning on the machine is to reset all the zero sensors. To do this, I'll move it closer to the end positions and start the end sensor search procedure. Okay, the limit switches are reset. Now we can start mounting the tooling. Now, I'll move the gantry out of the way so it doesn't interfere. The table is homemade, made from 40 millimeters. Plates, because the original factory work table made from extruded profile is absolutely useless. Here, I leveled it parallel to all the guides, and the deviation is less than 1/10 of a millimeter, which is perfectly fine for my needs. Since the part is a one-off, and making the tooling out of aluminum would not really be feasible. In this case, since the part is a one-off and making the tooling out of aluminum really isn't practical, it would be far too expensive. Plywood, especially for turning, will work just fine for this. I want to make a recess where I'll carefully place the workpiece and process it, securing it with screws to fix it in place. I use regular clamps for the plywood. Now I need to choose the right length for the threaded rod. I only cut the rod by about 3 threads, but that's more than enough because here, the thread being used is M10. I'm carefully securing the plywood in place, and the cutting resistance will be negligible compared to the strong clamping force. Now, I need to choose the most suitable spot for machining. I have to mark the 0 point, which is the reference origin, and bring the cutter precisely to that location. Then I need to select the cutter for which I wrote the control program. The fixture will be machined with 2 different cutters in sequence. These are 10 and a 6 end mill. Since this is plywood, I can basically use any of them. I don't have specific cutters for wood or plywood, but it doesn't matter. Let's change the cutter. Unscrew the old one. Here, we have it set up for aluminum, a 3-flute one. It's a shame to use it on plywood. Before clamping the cutter, you definitely need to check the protrusion. My maximum cutting depth is 24 millimeters. Here it's set to 25. Well, I just clamp it at 30 and that's it. Got it. Now I'll switch the control to the remote and bring the cutter to the 0 point. This is what our remote looks like. Forward and backward is the y-axis, left and right is the x-axis. For the height, I need to get exactly at the surface of the plywood. Now, I'm carefully lowering the cutter by 10 units, making small adjustments by hand. At the moment, it's caught, so I believe this height will serve as my 0 point for the z-axis. Next, I'll set up the air blower to gently blow the chips out of the groove, keeping the area clean. I'll turn off the oil feed so that only air is blowing. I've positioned the cutting tool precisely. Go to the right spot. Now I need to zero the coordinates. I do this with the G92 command, setting X0, Y0, Z. Well, let's make it 0.1. I'll take off another 10. Go a bit deeper. Now I need to load the control program. The setup is ready. I can now insert the workpiece into the selected hole. Alright, the setup is ready. I can now drive the workpiece into the selected hole. I made it just a bit smaller by a couple of tenths, so I can hammer it in and it will fit tightly. Everything is secured. I fixed the workpiece in place and changed the milling cutter. Everything is secured. I fixed the workpiece in place, changed the milling cutter, uploaded new control files to the cam, loaded them into the controller's memory, and started machining the duralumin workpiece. Whenever I run a new control program for the first time, I always set the speed to minimum, just in case I made a mistake somewhere. That way, if I made an error, I have the opportunity to stop the processing time and minimize any damage. I deliberately set a very shallow cut and a very low feed rate, carefully making sure that the workpiece wouldn't get ripped out of the plywood. To prevent mistakes and damage, I used a shallow cut and slow feed. After leveling, I secured the workpiece and processed it in sections. With a normal feed rate, I've carefully brought the workpiece to the desired thickness. Now, I want to secure it in place with screws. Before that, I'm going to drill a hole in the plywood so I don't accidentally split the bottom of the workpiece. By the way, I think Leka is doing a great job filming here. He's the one working on this project. Leka, why don't you tell us a bit about what you're doing?
Hello? What can I say? Unfortunately, I combined the epoxy incorrectly and it didn't cure. This hole here and this one, which goes all the way through. Epoxy failed. I must redo it.
I made a mistake. I'll fix it. It's finished so as not to keep the videographer here for another hour and a half while the final finishing is done. We decided to end the video here. In fact, the part on the other side will be almost identical to this one, except that the bearing seat will be of a larger diameter. Next week we will assemble this scooter completely, and then we can shoot a video of us testing it